NATO air doctrine has a $1.7 trillion blind spot, and on March 19th, Iran found it.
Iran's Army Air Defense Forces claim that they have targeted and destroyed another Israeli F-35 fighter jet in the skies over western Iran.
On March 19, 2026, a United States Air Force F-35A was conducting operations over central Iran during the third week of what the Pentagon had been calling Operation Epic Fury. It was struck by an Iranian surface-to-air missile. The aircraft sustained significant damage and made an emergency landing at a U.S. military facility in the region. The pilot survived. That is not the remarkable part. The remarkable part is how Iran tracked it. The F-35 never knew it was coming. No warning receiver triggered, no evasive maneuvers were taken, no countermeasures were deployed. The aircraft was flying a steady course when the missile found it. The pilot had no indication that anything on the ground was watching him at all. This was not a lucky shot. This was a doctrine. And what that doctrine exposes goes far beyond a single aircraft in a single engagement over Iran. 8 European NATO member states are currently operating or in the process of acquiring the F-35. They built their air defense architecture around the same assumptions that just failed over central Iran. The question now sitting on the desk of every European defense ministry is not whether to cancel their programs. The contracts are signed, the aircraft are being delivered, the training pipelines are running. The question is, what doctrine you build around a platform whose central advantage just had a documented, reproducible counter demonstrated against it in live combat. That is what this video is about. To understand what happened on March 19th, you need to understand what the F-35 was designed to do and what it was specifically not designed to address. The F-35 program is built around the concept of low observability, stealth. The aircraft's entire geometry is shaped to scatter radar returns. Its engine intake, its weapons bays, and its airframe surfaces are all engineered to minimize the signal that bounces back to a radar receiver. The effect is a dramatically reduced radar cross-section, meaning that high-frequency fire control radars, the kind that guide surface-to-air missiles, struggle to achieve a stable track on the aircraft at useful engagement ranges. The F-35 also carries onboard electronic warfare systems that monitor the electromagnetic environment around it. If a radar is painting the jet, the aircraft's warning receivers detect those emissions and alert the pilot. The pilot knows he is being tracked. He can respond. Iran's system emitted no radar signals at all. What the Iranians used was a passive electro-optical tracking system, infrared, a sensor that reads heat rather than radar reflections. The engine exhaust of an aircraft produces an enormous thermal signature. The friction of an airframe moving at speed through air generates heat across the fuselage. These are physical facts of aerodynamics and thermodynamics that no amount of radar-absorbing coding addresses. You can shape an aircraft to scatter radar waves. You cannot make it cold. A passive infrared system sits on the ground, emits nothing, and watches the sky for heat. There is nothing for a radar warning receiver to detect because there is no radar. The system is completely silent from the F-35's perspective. When that infrared track was handed off to the surface-to-air missile, the interceptor used its own imaging infrared seeker to home in on the aircraft's heat signature for terminal guidance. The F-35's warning systems were, by design, looking for the wrong thing. This is not a new technology. That is precisely the point. Infrared search and track systems, known as IRST, have existed for decades. Russia has them fitted to its Su-35 fighters. The Su-57 goes further. It was not designed with IRST as an added feature. It was designed from the outset to hunt stealth aircraft specifically by their thermal signatures, using passive infrared as a primary sensor mode, without emitting radar pulses that could be detected by an opposing aircraft's warning systems. That distinction matters. The Su-57 was built around the assumption that low observable aircraft would be present in its operating environment and that radar alone would be insufficient to engage them. China reached the same conclusion. The J-10C and J-16 both carry IRST systems. These are not experimental programs or developmental concepts. They are fielded capabilities deployed at scale across the air forces most likely to contest NATO airspace. What Iran demonstrated is something different in character, though identical in principle. A ground-based passive electro-optical tracking network feeding targeting data to a surface-to-air missile system. A country without a sophisticated air force, operating under significant pressure from one of the most intensive air campaigns in modern history, managed to engage a fifth-generation stealth aircraft using a detection method that the aircraft was never designed to defeat. and it did so for a fraction of the cost of what it hit. The F-35A cost between $80 and $110 million per airframe, depending on variant and delivery batch. The Iranian engagement system that struck it costs orders of magnitude less. This is what defense analysts mean when they use the phrase fiscal asymmetry. An adversary deploys inexpensive countermeasures to neutralize expensive assets, bleeding an opponent's resources over time without matching them capability for capability. The GAO recently revised the F-35's projected lifecycle cost upward to $1.7 trillion across the program's lifetime, driven by the extension of its planned service life and sustainment costs that the Air Force itself has acknowledged are currently unsustainable. When you place that figure next to a passive infrared tracker and a relatively low-cost interceptor, the arithmetic of the engagement becomes its own kind of statement. There is a second factor that made the March 19th engagement possible, and it has nothing to do with Iran's ingenuity. It has to do with American software delays. The F-35's Block 4 upgrade is a major software and hardware modernization intended to expand the aircraft's weapons compatibility and computing capacity. Block 4 is the update that allows the jet to carry and deploy several categories of advanced long-range standoff munitions. Standoff weapons are specifically designed to be fired from a distance well outside the effective range of enemy air defense systems. The logic is straightforward. If the aircraft can engage targets from 150 to 200 kilometers away, it never needs to enter the engagement envelope of a surface-to-air missile network in the first place. Block 4 was originally scheduled for completion in 2026 at a projected cost of $10.6 billion. That estimate now stands at $16.5 billion. The schedule has slipped to 2029 at the earliest, and even that timeline remains uncertain. The critical design review originally planned for mid-2025 slipped to mid-2026, and that milestone only closes the design phase. Manufacturing, testing, and fleet-wide integration all follow after that. Compounding the software delay is a propulsion problem. Pratt & Whitney's engine core upgrade, which is required to generate the additional power and cooling that Block 4's expanded electronic systems demand, has accumulated a $6 billion cost overrun and a 3-year delay of its own. The F-35 is running behind on both software and engines simultaneously, and those two delays are not independent of each other. One feeds the other. That delay does not stay inside the Pentagon. Every NATO operator flying the F-35 inherits it. The consequence is operational and immediate. F-35 pilots in contested airspace are currently limited in their standoff engagement options. Without the ability to strike from maximum range, they must fly closer to their targets. As an aircraft closes distance with a sensor, even a stealthy one, the geometry that makes radar cross-section reduction effective begins to break down. Low-frequency radar systems, multi-static detection networks that triangulate from multiple angles simultaneously, and passive infrared trackers all become more effective as range decreases. A software delay inside a program office in Fort Worth, Texas, put an American pilot within reach of Iranian ground defenses that he would otherwise never have needed to approach. That line belongs in any honest account of March 19th. The engagement was not purely a story of Iranian capability. It was also a story of American institutional failure. Procurement delays with billion-dollar cost overruns translated into operational exposure for a pilot flying a mission over hostile territory. The distance between those two facts, a program office and a cockpit, is exactly the distance that fiscal asymmetry is designed to exploit. Now map that onto the European procurement landscape, because that is where the long-term consequences of this engagement will be felt. 8 NATO member states have committed to the F-35 as the cornerstone of their tactical air power. The Netherlands was among the first to finalize deliveries. Norway and Denmark have completed their acquisition cycles. Belgium has 34 aircraft in service with 11 additional ordered in early 2026, a decision taken before the March engagement. Italy operates 90. Poland ordered 32 explicitly for high-intensity deterrence against Russia, configured for operations over Eastern Europe. Germany presents the most strategically complicated case. Berlin purchased 20 F-35As specifically to fulfill the nuclear sharing role within NATO, carrying USB 6112 nuclear gravity bombs under the alliance's burden-sharing arrangement. There is no alternative aircraft currently in the Bundeswehr's inventory certified for this mission. Germany cannot easily substitute another platform and cannot simply choose a different procurement path for these particular aircraft. At the same time, Germany remains a partner in the Future Combat Air System, the FCAS program developed jointly with France and Spain, intended as Europe's next-generation fighter. That program has accumulated its own delays and faces fundamental industrial disagreements between Airbus and Dassault over technology-sharing arrangements that have proven genuinely difficult to resolve. Germany is caught between a faltering European alternative that does not yet exist and a US-dependent system whose operational doctrine just shifted under live combat conditions. For Poland, the stakes are different in character, but no less pressing. The 32 F-35s ordered by Warsaw were procured precisely to operate in the airspace where Russia's IRST-equipped Su-35s and Su-57s are already deployed. The Eastern European theater, across the Baltic approaches and into Polish airspace, is an environment where Russian passive infrared tracking systems are not a hypothetical future threat. They are already there. The Su-57 was built specifically to engage aircraft like the F-35 in exactly that environment. What Iran demonstrated with a ground-based passive system is a capability that Russia has been fielding on its frontline fighters for years and has oriented an entire airframe design philosophy around. Poland bought the F-35 to deter and defeat that threat environment. The question of doctrine, of exactly how the aircraft operates against IRST-equipped adversaries, is not an academic one for Warsaw. It is the entire operational premise of the purchase. The U.S. response to this vulnerability is already visible in procurement decisions, and it tells you something important about where doctrine is heading. The Pentagon is accelerating development and production of the stand-in attack weapon, the SIAW. This is a high-speed munition designed specifically for the F-35 to destroy mobile air defense systems from within contested airspace before those systems can engage. The concept represents a shift in how planners think about the aircraft's role. The F-35 does not fly through the threat environment and rely on stealth to survive the approach. It identifies and destroys the threat at standoff range from 150 to 200 kilometers out and then penetrates into the cleared zone. The AARGMER, the Advanced Anti-Radiation Guided Missile Extended Range, operates against radar-emitting air defense nodes on a similar principle. Both systems are designed to address the same problem Iran demonstrated: mobile and passive surface-to-air systems that can survive a stealth aircraft's approach until it enters their effective engagement range. Beyond standoff munitions, the Pentagon is accelerating development of collaborative combat aircraft, autonomous drones designed to fly alongside the F-35 in contested environments. The concept positions the F-35 not as the primary penetrating striker flying into the heart of a defended zone and relying on stealth for protection, but as a battle management node coordinating a swarm of expendable unmanned systems that absorb the risk of the most dangerous phases of an engagement. The crewed aircraft stays at a safer distance. The drones go forward into the threat envelope. It is a doctrine built around accepting attrition of cheaper assets to protect expensive ones, and it represents a fundamental shift in how the aircraft's combat role is conceived. For European NATO members, this doctrinal evolution creates a secondary problem that receives almost no attention in public debate about the F-35. Integrating SIAW and AARGM-ER into European F-35 fleets requires U.S. export approval, separate procurement budgets, additional training infrastructure, and time. It does not happen automatically when a country takes delivery of the airframe. Belgium, Norway, and Denmark operate smaller air forces with leaner acquisition cycles. The gap between the F-35 as delivered and the F-35 as optimized for the threat environment that March 2026 clarified is real, and it does not close on its own. Collaborative combat aircraft bring their own integration requirements, their own costs, and their own dependency on U.S. program timelines that European operators do not control. Germany's F-35s are configured around the nuclear sharing mission with its own specific weapons integration requirements. The standoff suppression doctrine requires munitions integration that was not part of the original acquisition logic for those aircraft. The architecture is shifting underneath a procurement that was already locked in. What emerges from all of this is a picture that is not about a failed aircraft. The F-35 remains the most capable multi-role platform in NATO's tactical inventory. Its sensor fusion, its electronic warfare suite, its data-sharing architecture across coalition networks, its ability to share targeting data simultaneously with surface ships, ground batteries, and allied aircraft, all of that remains formidable and largely without peer. None of what happened on March 19th changes that fundamental assessment. What it changes is the assumption underneath the doctrine. Stealth was never invisibility. It was a probability reduction, a compression of the engagement window available to enemy air defense systems. Radar cross-section reduction makes it harder for a fire control radar to achieve and hold a track at the ranges needed to guide a missile to intercept. It buys time and distance. It degrades the performance of radar-guided systems. What it was never designed to do was address passive infrared detection, because passive infrared detection operates in a completely different physical domain. Iran did not defeat stealth. It bypassed the radar dimension of stealth entirely, using a detection method that stealth was never built to counter. Russia and China drew that conclusion years ago. Both have invested heavily in multi-sensor detection architectures that combine radar, low-frequency systems, multi-static networks, and passive infrared tracking into layered approaches that do not depend on any single detection method. China's J-20 is networked with high-altitude airborne control platforms that extend its radar detection range significantly. Russia built the Su-57 around the explicit premise that stealth aircraft would be present in its operating environment and that thermal detection was the answer. The strategic logic in both Moscow and Beijing has for years been oriented around the same insight that Iran applied in practical terms on March 19th. Do not try to outbuild stealth with better radar. Find the dimension that stealth does not address. For NATO, acknowledging this shift does not mean abandoning fifth-generation aircraft. It means building a doctrine that does not treat stealth as a complete solution and does not assume that any single capability advantage holds unconditionally across every threat environment. Fewer deep penetration missions into integrated air defense networks relying on stealth alone. More standoff engagement at distances that keep aircraft outside the effective reach of passive tracking systems. Greater investment in suppression of enemy air defenses as a prerequisite for operations rather than an afterthought. And serious, funded allocation toward the munitions integration and autonomous systems that make the standoff doctrine operationally real, rather than theoretically appealing for European operators. Whether NATO's European members have the procurement budgets, the munitions stockpiles, and the political will to build that doctrine is a question that remains genuinely open. The contracts for the aircraft are signed, the investment has been made. The harder work now is building the operational architecture around a platform in a threat environment that just demonstrated it is more contested than the doctrine assumed. The F-35 will remain the backbone of NATO tactical air power for the next 2 decades. That is not in question. What changed on March 19th is the operational assumption underneath it, and the next video connects directly to this one. Russia's air defense network along NATO's eastern flank, and what the F-35's evolving standoff doctrine actually has to work against across the Baltic approaches and into Poland. Subscribe so you do not miss it.